Well, in this part of the lecture, we're going to extend our knowledge of different acid-base theories. We've had Arrhenius acid-base theory, we've had Bronsted-Lowry acid-base theory, and now we're going to go to one that's a little bit different called Lewis acid-base theory. And this is the same Lewis from our Lewis dot diagrams. G.N. Lewis, remarkable chemist, contributed a lot to the knowledge of chemistry. And rather than looking at how H pluses move around, Lewis chose to look at how electrons move around to further extend our knowledge of how acids and bases work. So again, we mentioned how we had Arrhenius acid base. They kind of encompassed this amount of acids and bases, but there are still some things out here that had acid-base properties that Arrhenius theory couldn't account for. And then we had Bronsted-Lowry theory, and that kind of encompassed a lot more of the compounds that had acid-base properties that Arrhenius couldn't do. And now Lewis acid-base goes even farther outside of that. So everything that was an acid or a base by Arrhenius or Bronsted-Lowry is still an acid or a base on based on Lewis acid-base theory, but we're adding just some more things in there. So we mentioned at the start that the Bronsted-Lowry theory worked very well for describing how protons move back and forth during a reaction. But this idea of Lewis came about by looking at how do electron pairs move about. And so Lewis defined a Lewis acid as something that accepts a pair of electrons to form a new bond, and a Lewis base became something that donates a pair of electrons to form a new bond. Now you've got to make sure that you don't mix up the accepting and donating of Lewis acid-base theory with the accepting and donating of Bronsted-Lowry theory. Okay, Bronsted-Lowry theory had a base accepting an H plus, accepting a proton, and an acid was donating a proton. Whereas here an acid is accepting a pair of electrons and the Lewis base is donating a pair of electrons. So you just want to make sure that you don't mix those up. And so the new substance that forms when you have a Lewis acid-base reaction take place is something called an adduct. Oh, look at that. It's a duck. Adduct. Yeah, more Camtasia humor here. All right, so our acid and base labels still apply, and we can take some of our acid-base reactions that we've looked at so far and look at them from Lewis acid-base theory. They're going to look the same, but we're just describing them a different way. So if we look at a reaction of H plus and water here, so we've got our Lewis acid, H plus, our Lewis base, water here, and we form our adduct, H3O plus. We've been throwing H3O plus around in our reactions like crazy, but how does that really come about? Well, if we have an acidic hydrogen on a compound, the water can come along and say, hey, H plus, do you want to form a bond? And H plus goes, I can't form a bond. I don't have an electron to donate into that covalent bond. And the water says, well, you know what? I've got two extra pairs hanging here, so I will donate both electrons for the bond, and then we get a nice bond forming between the oxygen and that H plus, and so we call that an adduct. Now the bond that forms between them is called a coordinate covalent bond, but it's no different than a regular covalent bond, whether both atoms shared an electron and formed a covalent bond, or if one atom put in both electrons and formed a covalent bond. There's no difference between the bonds. You can't identify them in any way. They are identical. The only thing different between them is how they form. We see the exact same kind of behavior here between an H plus and an H3. An H3 has this lone pair right here. It can use that lone pair to form this bond between the H plus and the NH3, or the nitrogen atom on there, and we get the NH4 plus. So it's what's called a coordinate covalent bond. It explains how some of these bonds can form in some of these some of these complexes or some of these compounds. Now, those kind of compounds weren't the reason that we looked at Lewis acid-base theory. They're not the reason that Lewis acid-base theory came about. It was really the behavior of metal ions, because metal ions in solution, if they are small and have a high charge, if you put them in water, they often develop acid properties. You have an acidic solution just with a metal ion in there. And the question becomes, well, how do metal ions have acid or base properties? They don't even have an H+. They don't create OH- ions in the same way that Bronsted-Lowry said they would. So we needed a new theory to describe how they worked. We also see where metals form bonds with lots of Lewis bases like water or ammonia. And we see that water and ammonia have lone pairs to form that coordinate covalent bond. And as it turns out, lots of metal ions, particularly transition metal ions, have a lot of empty d orbitals where they can accept electrons into and form a bond. So here's an example of a coordinate covalent bond between a copper ion and ammonia. Actually, it can form up to 4 bonds with ammonia, and you get what's called a copper ammonia complex. Notice that the charge remains, so we've just got the Cu2 plus in water. It's a very light blue solution. When you put ammonia in there, you now have a copper with 4 ammonias on it. It still has that 2 plus on there, so this is called still an ion. It's called a complex ion, which indicates it's more than just that metal ion. So we call those a complex ions. Okay, so complex ion. Lots of different metals form complex ions. If you put transition metal ions or salts of transition metals into an aqueous solution, generally you will have some sort of color. These colors aren't very good. You get a very faint pale yellow with iron. You tend to get a reddish pink color, sometimes orangey from cobalt, kind of a minty green with nickel, or a very pretty blue with copper. And if you change out what the metal complex is attached to, you can actually change the color of the solutions quite easily. So again, we're not going to do very much with these Lewis acids, bases, or these metal complex ions. Again, if you go on to further chemistry courses, particularly inorganic chemistry, you start looking at these types of interactions in a lot of detail. So I give them to you here so that if you choose to go on and take higher levels of chemistry, you'll know that you've seen these before in a previous class. So if you have any questions on this, let me know.